Well, good morning, everybody. So, just before I begin, another reminder, please don't forget to turn in your homework. You could just bring it up after class if you'd like. I'll post the solutions outside my office like I do every Wednesday. Also, I have not seen the videos from the previous lectures yet, so I actually swung by Mr. Henderson's office, who's the director of Media Vision, and Henderson, I think that's his last name. Actually, it doesn't even matter. Anyway, we talked, so he said that, oh yeah, usually we can get that out within a week, and apparently there's just some miscommunication. So he understands, and as soon as they're made available to me, I'll post them on Blackboard. But as of right now, I don't have anything, so just keep your eyes peeled. Hopefully they'll show up eventually, and I'll let you know when they're there. So we're now talking about the Brayton cycle, right? And last time really was more of a review, just talking about the general nature of the Brayton cycle. We looked at both the ideal and non-ideal simple Brayton cycle. We looked at the situation where we could use either constant or variable specific heats. Certainly variable specific heats is more accurate, and that's a method that you should understand how to utilize. On an exam situation, I'm not going to just give you the option of choosing whatever method you want. I will specifically ask you to use either variable or constant specific heats, but certainly variable specific heats is more important, and you definitely have to understand that method of solution. Nonetheless, what I want to do now is go through an example problem, and this one's actually out of your textbook, edition 8 of your Cengel Boles book. Some of my example problems are from other versions of the textbook, and I will put them on the board. And I think I'm pretty sure that I already put them all, every one of them, on Blackboard. So, if you want to just print out those images rather than write down the problems, then you can certainly do that. Nonetheless, here's our first example problem that deals with this material. We have a simple Brayton cycle that uses air as a working fluid. You're given the pressure ratio of 10. By the way, I don't know why they had to tell us that air is a working fluid. Well, we're only dealing with air standard cycles, so clearly air is a working fluid. The pressure ratio is 10. We have the minimum maximum temperatures in the cycle, so please note that this would correspond to 0.1 and 0.3, right? 1 would be the ambient air conditions going into the compressor. 3 would be at the end of the combustion process, which is where your temperature is always going to be at its highest. We're given isentropic efficiencies for both compressor and turbine, and we're trying to figure out the air temperature at the turbine exit and the net work output and the thermal efficiency. So as we start this particular problem, let's just start with an illustration. Personally, I always like to start with a TS diagram. We should show the minimum and maximum pressures within the cycle. We know that state point 1 represents the beginning of compression. We know that since we're given isentropic efficiencies, we have to recognize that we're not only finding the assumed ideal exit conditions from the compressor, which would be point 2s, but we have to use the isentropic efficiency along with point 2s data to get the conditions at point 2 actual. So let's show both of those on this diagram. We have our heat input process up to point 3. We have expansion through the turbine as we produce work down to point 4. Again, if it were ideal, then we'd have 4s directly below point 3. It's not. So we have our actual 0.4a, and this then would represent the thermodynamic cycle on the TS diagram. You could show it on a PV diagram too if you want to, but the TS is just customary. And then also let's make sure we indicate all of our appropriate data. Certainly we know that it's air. We're given the pressure ratio of 10. Again, this is a pressure ratio, right? Not a volume ratio like we would have used for Otto and diesel cycles. Minimum and maximum temperatures are given. So T1 is 295, and that's in Kelvin. And 1240, also in Kelvin. That's nice that they're in Kelvin. That means we don't have to convert from Celsius into Kelvin. And we're given the isentropic efficiencies of 83% and 87% respectively. So 0.83 and 0.87 are given to us. And we're trying to find the air temperature at the exit of the turbine. So that's T4. Really, we have to put the 4A just as a reminder. They're not asking us for what the temperature would be if it were an ideal turbine, right? They're asking us for the actual turbine exit temperature. So T4A is what we need. We need the net work output. So work net is unknown. And the thermodynamic efficiency. This is also unknown. By the way, I'm not completely happy with the wording of this problem, not just the fact that they told us it's air, which was obvious, but they say the net work output. They really mean the net work per unit mass output, or I should say the net work output per unit mass. So we don't have any data on volumes. We have no way really to determine the mass that's moving within this cycle. So there's no way we could actually calculate the net work output. All we can do is calculate the work on a per unit mass basis. So, you know, a little bit confusing perhaps, but nonetheless, that's really what the author intended. So with all this, how do we approach the problem? Well, frankly, they don't specifically tell me that I need to use constant or variable specific heats, yet I don't want to spend the time to do it both ways. So let's just use variable specific heats. So the process is really quite straightforward. I mean, we've seen these kind of problems before, right? So the first thing is that at T1, we're going to go into table A17, and we're going to look up PR1. Of course, we're also going to need the internal energy data at that point. So we'll also find U1. And I'm just going to go through the methodology in general form first, and then I'll plug in all the numbers in a moment. Once we have this data at point 1, now we recognize that we have a isentropic compression process from 1 to 2s. So therefore, the pressure ratio, which is just P2 over P1, is also equal to the ratio of relative pressures from 1 to 2s. So P2 over P1 is PR2s over PR1. And keep in mind, this only applies for the isentropic process, right? We can't use this to find the pressure ratio. I'm sorry, we can't use this to find the relative pressure at point 2 actual. This only allows us to find 2s, the relative pressure at the ideal exit from the compressor. But nonetheless, this gives me the ability now to find PR2s. So I'll just leave a little space to plug in the numbers here in a moment. And then we know the compressor's isentropic efficiency is 0.83. And we know that this is the ideal over the actual work. And of course, that would mean the ideal over the actual enthalpy change. And I'm sorry, I have to make one little correction. I don't know why I put U1 there. I mean, if we have a closed system, like an Otto or diesel cycle, then it's internal energy data that we need. But this is not, right? This is a steady flow series of devices. It's enthalpy data that comes from the first law. So please just get rid of the U1 and replace it with an H1. Anyway, ideal over actual work is going to be H2S minus H1 over the actual enthalpy at point 2, H2A minus H1. So we should be able to find that. And by the way, once we've found PR2S, we are going to have to go back into our property tables and look up the enthalpy at 2S. So I really missed something in here. So at PR2S, back into A17, and that gives me H2S. And again, we'll look up the numbers here in just a moment. Okay. And nonetheless, solving this problem will allow me to find H2 actual. And then we're going to do exactly the same steps, but for the turbine from 3 to 4. So at T3, we're going to go back into table A17, and we're going to look up PR3 as well as H3. Then we're going to recognize that the pressure ratio is P3 over P4, which is PR3 over PR4, and again, S, right? This only applies for the isentropic process. Once we found PR4S, we're going to go back into table A17 and look up H4S. And then once we have H4S, we're going to apply the turbine's isentropic efficiency, which is 0.87. to get H4A, right? This is the actual over the ideal work now. So this is H3 minus H4 actual over H3 minus H4S. So this will then allow me to find the actual enthalpy at point 4. And frankly, once we have all these enthalpy terms, then it's just a matter of finding all the other data we need. So for instance, once we've found H4 actual, which again we'll look up in a minute, then we're going to go back into table A17 at this actual enthalpy, and this will allow me to find T4. Now, T4 is the actual temperature at 4, right? T4A, so just as a reminder, don't forget your little A there. So this gives me that temperature. And then in order to find the net work output, it's really just a matter of finding the difference between the work done by the turbine and the work required by the compressor. And again, you could put little subscripts A here just to remind you that we're talking about the actual work terms. And so this is H3 minus H4A. And then we subtract from it the magnitude of the work required by the compressor. And this will allow us to find that result. And then last but not least, the thermal efficiency should be pretty straightforward. Just the net work over the heat input. The net work we'll have from above. The heat input is just the heat input from points 2 to 3, which we know is just H3 minus H2A. So again, once we plug in all the numbers, we should be able to get that result. So hopefully you remember doing all of this in your previous thermodynamics class. So let's go through the numbers. Now, I could put up table A17 on the board here. I don't think I will. I think at this point, hopefully you all understand how to use that particular table. So when we go into the table, we'll find that PR at point 1 is 1.3068. And we'll find that the enthalpy at point 1 is 295.17 kilojoules per kilogram. Having PR1, again from the equation below, we just plug this in down below. And this allows me to find PR2S. And for PR2S, we get, where's my PR2S? Oh, there it is, 13.07. Well, I mean 13.068 really, right? Okay, so there's the relative pressure at the ideal discharge from this compressor. And then we have to go into our table, and at this relative pressure, just simply look up the enthalpy. Now, we have to do this by interpolation, right? It's not likely we're going to find this exact value. So just using linear interpolation, we'll find the value of H2S, and that's 570.26 kilojoules per kilogram. And now we just plug all these numbers from above down in below. And again, in the interest of saving time, I'm not going to actually plug in and chug away with the numbers. We'll just know how to solve it, right? H2S from above, H1 from further above. We find the actual enthalpy, therefore, as 626.60 kilojoules per kilogram. Right. So we have our enthalpies at 1 and 2. And again, do the same thing from 3 to 4. So at point 3, we've got 1240 Kelvin. We go right into table A17. And we get 1324.93. Whoops, that's my enthalpy. The relative pressure is 272.3. The enthalpy is 1324.93 kilojoules per kilogram. Okay. So again, we have our pressure ratio. That's equal to 10, as has been given. 272.3 over PR4S. And then PR4S can be calculated pretty easily. And this is just going to be 27.23. And then we go into our table. And again, by interpolation, we get the enthalpy at 4S, which is 702.07 kilojoules per kilogram. And again, once we go through the mathematics, just plug everything in below. And that allows me to find the actual enthalpy, which is 783.04 kilojoules per kilogram. So we have all of our enthalpy terms. Now let's just use those enthalpy terms to find the other data that we need. So we can look this up, again, by interpolation at this value of enthalpy. We'll get that the temperature is 764.4, and this is in Kelvin. So you can leave it in these terms if you want to. We plug in all the enthalpy terms, and we would find that the net work is 210.46 kilojoules per kilogram. And last but not least, we just plug the numbers in from above. Again, I'll let you plug in H3 and H2A. The heat input can be calculated. It's actually 698.3. But if we plug in the math, we end up with 0.301. Or if you prefer, you can write it as a percent, 30.1%. And that's this example problem. So, pardon me, are there any questions on this particular problem? Okay, hopefully you find it pretty straightforward. So one other thing that we haven't yet talked about just with regards to Brayton cycles is something that's called the back-work ratio. And I do want to discuss it very, very briefly, although I'm not going to use it in the context of this problem. But nonetheless, we're done with this for the time being. Okay. So it might be noted that in a compressor, there's a lot of work that's required. And what the back-work ratio does is just give us a measure of how much of the work produced by the turbine is actually going to be required by the compressor. Okay? In some problems, most of the work produced by the turbine is actually required by the compressor, and you get very little net work output. Sometimes very little of the work produced by the turbine is actually required by the compressor, and you get a lot of net work output. So it does make a certain amount of sense to look at this term called the back-work ratio. Okay. So this is just R with the subscript BW for back work. And this is simply defined as a ratio of the work that's required by the compressor over the work that is produced by the turbine. So this is the actual compressor work divided by the actual turbine work. Okay. So this is a useful parameter in many problems. Certainly our main interest is producing a lot of net work for the usual reasons, right? So that we can sell that work to our customers as electricity or provide thrust on a jet engine or whatever it might be. Nonetheless, this is something I just wanted to at least expose you to. You will be asked to find the back work ratio in certain problems. So now let's move ahead. We've looked at the simple Brayton cycle. We looked at it both in the ideal and non-ideal case. And now what we need to do is start making the various modifications to the Brayton cycle in order to improve the performance. And when I say improve the performance, we're really talking about increasing the thermodynamic efficiency. And there's various ways that we can do that. Again, with the understanding that increasing the thermodynamic efficiency is not something we do just because it's fun. We want to sell the most work as possible. I mean, that's the whole intention of using an engine. You know, minimize the heat input that you pay for and maximize the work output that you get your benefit from. So what can we possibly do in order to improve the thermal efficiency? There's various things that we can do, but three things come to mind, and these are the three things that we're going to talk about. The first one is by using what's called a regenerator. We waste a whole lot of heat as we reject exhaust gases at point 4, or if you will, as we just transfer heat out of the air from point 4 as it cools back down to point 1. Why? Why do we have to do that? Why don't we take that waste heat and simply run it through a device that preheats the air that's being used within the combustion chamber? If we can preheat that air, then less heat has to be purchased, right? Less fuel has to be purchased, less heat. That's a good thing, right? That improves our thermodynamic efficiency and maximizes our benefit, minimizes our costs. So that's one thing we're going to talk about. Another thing we can do is see if there's some way we can let's say, minimize the work that's required by the compressor. In fact, I think it's section 710 of your textbook, maybe it's 711, I think 710, which talks about minimizing compressor work. It turns out that instead of going through a single stage of compression from point 1 to point 2, if you actually compress in multiple stages, that will actually minimize the amount of work required by the compressor. So that's another thing we can do. And the third thing we can do is look at the turbine and ask ourselves, is there some way we could produce work in the turbine that is greater than the amount of work we would see from the simple cycle? And again, the answer is yes, and it's really for the same reasons as we looked at minimizing compressor work by compressing in stages. It turns out if you expand in multiple turbine stages, then you can also maximize the amount of work output in that turbine. So we're going to look at all three of those things. One is called regeneration, one is called intercooling, one is called reheat, and we'll just start with the Brayton cycle with intercooling. Okay. So this is something that shouldn't really have been covered in your ME 301 class, and it's all new material now. I'm sorry, I said intercooling. That's the second thing we're going to look at. Regeneration will be the first thing. So let's keep it in the same order as is done in the book. So with regeneration. Okay. So let's just look at a schematic. We're going to enter the compressor at point 1, and we're going to come out at point 2. And here, instead of going directly into our combustion chamber where we add heat, here we're going to go into a heat exchanger. And this heat exchanger has a name, and it's called a regenerator. Okay. Again, it's just a heat exchanger. We're taking heat out of one stream and putting it into the other. Now, the bottom set of tubes in the heat exchanger, the regenerator, is going to come from the exhaust gas, right? It'll come from point 4, and we'll get to that in just a minute. The top line, of course, is the air that we're going to be using for the heat input process. So we come out of our regenerator, and typically we'll just give it a new number, 5. I'm not going to call it 3, because 3 will always represent what goes into the turbine. Well, will generally represent what goes into the turbine. So here's point 5. That comes out of the regenerator. And now we go into our combustion chamber where we have heat input. So maybe I'll show work input, regenerator, heat input. We come out of the regenerator at point 3. We go into our turbine where we get our work output. And now again, I should probably use a WC and WT just to represent the compressor and turbine work. Nonetheless, we get our work output. We leave the turbine at point 4. And again, instead of just dumping this heat into the environment through the heat rejection process, let's recover that heat. Let's bring it into the regenerator and take some of the heat out of the exhaust gas and dump it into the incoming air. So we now come out of the regenerator here, and we've now dropped down to a new exit temperature. We'll call this 0.6. And now we finally go into our environment, which is our final heat exchanger, where we have our heat rejection, our heat output. Okay. I like to show the environment just kind of as a big cloud. You could show it as a heat exchanger or really anything you want, but it's a closed system. We're not really dealing with the environment, but still, I show it this way. So does everybody understand the basic process here? How we're taking what would otherwise be wasted heat and transferring it to a part of the system where we could utilize that heat, and therefore we have less heat input in the combustion chamber, less fuel to purchase, lower heat input, and therefore higher thermal efficiency. Now, one thing I do want to note, yes, there is heat exchange within the regenerator. Obviously, it's called a heat exchanger, but we don't include any heat in or heat out. Keep in mind that these heat transfer terms, in fact, the work terms for that matter, have to cross the boundary of the system. The regenerator is entirely within the system, right? There's no heat coming in from an external source. There's no heat being rejected to an external sink. We simply have an internal exchange of heat. Perhaps another way of thinking about it is that the amount of heat lost by the combustion gases, well, the air from point 4, is exactly equal to the amount of heat gained by the regenerator, or gained by the air moving through the regenerator. So there's a net heat transfer of 0 here. There's no heat crossing the boundary anyway, but nonetheless, this is just one way to think about it. So we're still going to have the same terms in our various equations. but they're just going to be calculated a little bit differently. Now, this perhaps should also be shown on a TS diagram. And just for the sake of illustration, I'm just going to show this as if it were an ideal cycle, but certainly we don't have to have an ideal cycle, right? We could have a non-ideal cycle. We could utilize non-ideal behavior in the turbine and compressor. In other words, use the isentropic efficiencies. And we'll certainly get to that eventually, but not quite yet. So we start here at point 1. I'll just put ideal. We compress up to point 2, and these are along 2 constant pressure lines. We now have internal heat exchange up to point 5. We now add heat up to point 3. So here's our heat input. We now do work. And here I have to be pretty careful. I want to make sure my temperatures are OK. And I think they're OK. I think this diagram still shows that what leaves at point 4 is actually greater than point 2. I think my dot here at point 5, I should actually lower it just a little bit for accuracy. Nonetheless, here's point 4. And then we exchange our heat. We get back to point 6 as we reject heat through the regenerator. And then finally, we have our heat output from 6 to 1. Okay, so this is what the process would look like. Now, as you're first reading about this in your textbook, they talk about something called a perfect regenerator. And if we talk about a perfect regenerator, then what that really means is that there's no losses in the heat exchange process, which quite frankly never occurs in the real world. In the real world, you're never going to be able to heat up the incoming air from 2 to 5 all the way up to the temperature of point 4. I mean, that just can't happen. If it were a perfect regenerator, we could say that. We could say that the temperature at point 4 will equal the temperature at point 5. We could also say that the temperature at point 2 is going to equal the temperature at point 6. But that's only for a perfect regenerator, and we can't really achieve that. It's impossible. None of you have had a heat transfer course yet, but it should make sense that you can only have heat transfer if there's a temperature difference, right? If the temperatures are the same, there's no possibility of heat exchange. So how are you ever going to get the temperature at 5 all the way up to the temperature at point 4? It just can't happen. The temperatures would be equal, and you'd have no heat exchange. So this is the perfect regenerator. However, in a real regenerator, well, we would find that the temperature at point 5 has to be somewhat less than the temperature at 4. Whoops, T4. And for that matter, the temperature at point 6 can't drop all the way down to the temperature of point 2, so T6 actually has to be a little bit higher than T2. Okay. So we're never really going to look at we're never really going to look at a perfect regenerator because they're not possible. It's the real regenerator that we're going to look at. So basically, this is our regenerator. Okay. Now, what about the equations that one would use? Well, quite frankly, the equations are the same. We're still interested in finding such things as the thermodynamic efficiency. We know the thermodynamic efficiency is still the net work over the heat input. We still know that the net work is simply the difference between the work done by the turbine and the work required by the compressor. It's still a Brayton cycle, so the net work is going to be H3 minus H4. That's the work out of the turbine. And then minus the work into the compressor, which is H2 minus H1. And of course, if we had isentropic efficiencies, I'd write H4A and H2A, but we're not dealing with that quite yet. And then as far as the heat input, well, that's the only thing that really changes, right? Instead of adding heat all the way from point 2 to point 3, we're only adding heat now from point 5 to point 3. So the heat input is just going to be H3 minus H5. And therefore, the thermal efficiency is just H3 minus H4 minus H2 minus H1, and then divided by H3 minus H5. So this is the general equation that we would have to utilize in solving these problems. Now, I guess I should note that if one were to solve using variable specific heats, using actual enthalpy data from table A17, you would use these equations directly, right? On the other hand, if we have constant specific heats, then we'd have to replace all the delta H terms with Cp times delta T terms. And of course, within the thermal efficiency equation, the Cp's are all going to cancel. And you get an equation that looks like this, but only includes temperature terms. Okay. Now, we'll get into this more in just a moment. So now the question becomes, what's next? How do we solve these problems? And there's a real issue that we have, because how do we calculate the temperature or the enthalpy at point 5? It doesn't come from thermodynamics. There's no thermodynamic equation that we would utilize to find the enthalpy at point 5. It actually has to come from heat transfer analysis in that heat exchanger, that is the regenerator. So we don't have the background to really talk about heat transfer and determine the relationship between the effectiveness of the regenerator and the actual temperature changes or enthalpy changes. So we have to be given that data. So we can't find our conditions at point 5 unless we have some information from heat transfer. And that information is going to be given to us as what's called the regenerator effectiveness. So we can't find H5 or T5 from thermodynamics. Okay. We need a heat transfer relationship. In this heat exchanger, that is in the regenerator. Okay. And that relationship is again called the regenerator effectiveness. And the effectiveness is just given as the Greek letter epsilon. Okay. And it's simply defined as the actual heat input to the air in the regenerator dividing by the maximum possible heat input to the air in the regenerator. And when I say air, I'm talking about the air moving from point 2 to point 5. So the actual heat input to air in the regenerator, and I'll just abbreviate regenerator as regen, divided by the maximum possible heat input to the air in the regenerator. Well, fortunately, these heat input terms are things we can calculate, right? I mean, it's still heat input. We're still going to use the first law of thermodynamics for a steady flow process. We're still going to ignore kinetic and potential energy changes. We'll note that a heat exchanger is a passive device, right? There's no work associated with it, no work associated with rotation or, you know, like we'd find on a compressor or turbine, no mixing work, nothing like that. So the fact is that the heat input in the regenerator is the same enthalpy change that we would have already seen for any other process in this cycle. Of course, the actual heat input is going to be from point 2 to point 5. So this is H5 minus H2. The maximum possible heat input would be if we're able to heat the air up from point 2 all the way up to the temperature of the exhaust coming out of the turbine all the way up to point 4, right? I mean, again, we can't achieve that, but we can at least try. So this is going to be H4 minus H2. Right? So this has to be utilized, okay? We're going to go through our Brayton cycle in exactly the same way that we've already talked about. Whether it's ideal or non-ideal doesn't even matter. We're still going to go through a compression from 1 to 2, perhaps 2s and 2a. We're going to go through expansion from 3 to 4, again, perhaps 4s and 4a. But ultimately, we're going to need to find the enthalpy at point 5, right? Without the enthalpy at 5, we can't find the thermodynamic efficiency. Right? We need that enthalpy at 5, and the way we find it is through the given value of the regenerator effectiveness. So that's always going to be given to you, and this is the equation we use. We'll solve it for H5, and, well, that would be that. Now, again, if we were using the method of variable specific heats, all these equations are valid as shown on the board. So variable specific heats, use equations above. if we have constant specific heats, I guess I should turn that back on. Uh-oh, that's not right. Oh, so this turns on one light in the very back of the room. That doesn't help. Okay, so if we have constant specific heats, well, then our equations are ever so slightly different. Again, we know how to do this, right? All the enthalpy changes become Cp times temperature changes. So for instance, the net work is going to be Cp times, well, T3 minus T4 minus T2 minus T1. The heat input is going to be Cp times, well, instead of H3 minus H5, it'll be Cp times T3 minus T5. And then, of course, the thermal efficiency is just going to be the ratio of the above. The Cp's are going to cancel. And we just get equations entirely in terms of temperature. Okay. And of course, we're also going to have to make a modification to the regenerator effectiveness. But it, too, is a simple one, right? I mean, Cp delta T in numerator and denominator. The Cp's are going to cancel. Oops. And everything becomes a function of only temperature. So T5 minus T2 or T4 minus T2. So these are the equations that we would use if we happen to have constant specific heats. Okay. And then lastly, I should also note, well, how does all this vary if we have a non-ideal cycle? It doesn't really change much, right? So for a non-ideal cycle, well, again, how do things change? Not much of a change. It's just that we have to use the isentropic efficiencies, right? I mean, still, we're going to have the net work, but oh, by the way, I should note that this does not specifically deal with constant specific heats. I'm just talking in general again about this type of cycle. But nonetheless, for a non-ideal cycle, the net work is still just going to be found using the same equations that are over here, but we're going to use H4 actual and H2 actual, right? So we'll have H3 minus the actual enthalpy at 4, and then subtract from that the actual enthalpy at 2 minus H1. So same equation, but with the little subscripts A. Heat input term doesn't change at all. Still just H3 minus H5. The thermal efficiency is, again, just the ratio of the two above. So I'm not even going to bother to spell it out now. I'll let you just plug the numbers in above. And of course, regenerator effectiveness is also going to change just a little bit. In the numerator, well, we want to use H2A. And of course, in the denominator, we want to use H4A and H2A. So H5 minus H2 actual over H4 actual minus H2 actual. Okay. And of course, if this were the situation where we have variable specific heats, then these are the equations you'd use directly, right? Okay. On the other hand, if we have the constant specific heats, well, again, these just change into Cp times temperature ratios. So, I'm not even sure I absolutely need to write this down at this point, but I will anyway. So T3 minus T4A minus T2A minus T1. And then the heat input is Cp times T3 minus T5. And the thermal efficiency, still the same. Network over heat input. But again, the Cp's are going to cancel, so everything is just going to be in terms of temperatures. And we get a T3 minus T5 in the denominator. Okay. And of course, the regenerator effectiveness, well, like we saw over here, we're just going to replace the enthalpy change with Cp times the temperature change. Cp's are going to cancel. So T5 minus T2A over T4A minus T2A. And these then would be the equations that we would use. Now the methods of solution are essentially identical. We're still going to go through the isentropic compression and expansion processes. Nothing really changes much. You know, the only real change, again, is the way we find these enthalpy terms. Now, should I have rewritten the TS diagram? It wouldn't hurt. I mean, we don't absolutely have to, but you know, maybe I will, because I can do it pretty quickly. I'll turn these solid lines into dashed lines. Here's T2S. Here's T2A. Here's 4S. And here's 4A. And this would then, of course, apply to our situation where we have a regenerator, but a non-ideal cycle. So I would just call this non-ideal. And now we have a TS diagram that represents the non-ideal case that includes a regenerator. Okay. So I would like to go through an example problem. And actually, one thing I should note before I even go through the example problem. In your textbook, there's an equation for the thermodynamic efficiency of a Brayton cycle with a regenerator. But in my opinion, the author doesn't make it real clear that that only applies if we have a perfect regenerator, and it only applies for the situation where we have constant specific heats. So I just want to make sure we understand that in the book, they give us this equation. So this is the equation that's presented in the textbook. But again, it only applies to the case where we have a perfect regenerator and ideal gas with constant specific heats. Okay, so you know, often as students are doing their homework, they see this equation and they don't perhaps think it through and recognize where this actually comes from. In other words, you can't use this equation, right? We're never going to look at a perfect regenerator. I mean, they don't exist. Why bother? Let's just look at the real regenerator with effectiveness given. So, well, I'm tempted to just put a big X through it, but I'm not going to. I'll resist. So let's look at an example problem. First, any questions just in general about this? Yes?
T1 over T3?
Yes, T1 over T3. So, why don't we just redo problem 983? So it's the same problem that was on the board earlier, but with a regenerator having an effectiveness of 82%. Sometimes effectiveness is also given in percentage, although you certainly have to use fractions in your analysis. So you'll see it written both ways. So if we go back to that previous example problem, I'm not going to bother to put it back on the board. The first thing I want to note is that 95% of the problem is identical to the one we already did, right? We're still going to go from 0.1 to 0.2s. We're still going to use the efficiency of the compressor to go from 2s to 2a. Previously, in the earlier example, we just went from 0.1 to 2, but really our new 0.2s is the same. I'm sorry, take that back. We did do a non-ideal case, right? So yeah, this would be identical, right? There's no difference. So we still are finding the data at 2a. So that's identical. From 3 to 4, also identical, right? Nothing has changed in the expansion from the turbine. Still have the same inlet conditions, same pressure ratio. We still find enthalpy at 4s and enthalpy then at 4a using the appropriate isentropic efficiency. So nothing is different, okay? The only thing that's different, and I mean it, the only thing that's really different here is using the regenerator effectiveness to get H5 and then using that to modify our heat input term so we can get the proper value of thermodynamic efficiency. So exactly the same, except use effectiveness in order to get H5. And then we use H5 to get heat input and thermodynamic efficiency. So that's nice. That'll save me a whole lot of time. In fact, that's why I've chosen to just redo the same problem. I mean, why do the same thing all over again? So 1, 2, 3, and 4, identical. So let's just finish this problem. We're given a regenerator effectiveness of 0.82. Whoops. And again, based on our definitions, we know this is going to be H5 minus H2A over H4A minus H2A. So we just plug in the numbers. H2A we found earlier as 626.6 kilojoules per kilogram. H4A we found as 783.04, and then minus 626.6 kilojoules per kilogram. And therefore, we find the enthalpy of 0.5, and it's 754.88 kilojoules per kilogram. We can now find the heat input. So H5 minus H3 minus H5. So the heat input becomes 0.05 kilojoules per kilogram. And we can then find the thermal efficiency. By the way, the net work doesn't change, right? The net work is only a function of the compressor and turbine work, so that hasn't changed. So the thermal efficiency, again, is the net work over the heat input. The net work was 210.46 kilojoules per kilogram. Again, same as before. The heat input is the only thing that's changed. And you can see that it does drop, right? The previous heat input we found is 698. And this is 570, so I mean that's almost a 20% drop of the heat input. And our thermal efficiency should rise accordingly, and this goes up to 0.369, or 36.9%. Okay, so this is just a, pardon me, one example anyway, of an ideal gas with variable specific heats problem for a non-ideal Brayton cycle with the regenerator. So any questions on this problem? Okay, hopefully you see it's pretty straightforward. Yeah?
Kind of just in the general way that we've been drawing the TS diagrams for the Brayton cycle,
Right.
normally it doesn't look like 0.4 would be above 0.5 or 0.2.
That's a legitimate statement. All I can really say is it just has to do with my accuracy in creating the diagrams. I mean, in reality, often you'll find these constant pressure lines to be quite a bit steeper than I've shown. And you know, that's why I had some issues as I was drawing points 4 and 2 and 5 just to make sure everything seemed correct. But no, I mean, in reality, you know, you'll have something more like this. So you have a pretty significant temperature difference. So you can actually heat up quite a bit to 0.5 and still note that it's below 0.4. The heat rejection can come down quite a bit, down to 0.6, yet still above 0.2. So it's really just an issue of accuracy in my diagrams. Okay. Any other questions before we move ahead? Good. So this brings us then to our second type of problem, which are problems involving intercooling. So now let's look at a Brayton cycle with intercooling. So again, what does that mean? Now, frankly, I very briefly mentioned what intercooling was. We're simply going to compress in stages. But let me give you a little more information on that. First of all, there's a couple of reasons why we might want to do this. So first, let me just note that this involves compression in stages with cooling in between compression stages. Okay, so even before I discuss this, if we were to look at a TS diagram, and let's just show the constant pressure lines. There's some maximum and some minimum pressure in the cycle. What we're going to do is we're not going to compress all the way from point 1 up to point 2. And again, for illustration, let's just look at the ideal case so we don't have to really mess with isentropic efficiencies at this point. But nonetheless, we're not going to compress from point 1 to point 2 in one stage. We're actually going to go through more than one stage. So what we'll typically do is compress to some intermediate point. So let's just get rid of that 2 that I put down there, because that's not where we want to go. We're only going to compress to an intermediate point, which is point 2. And this is actually at an intermediate pressure. So let's just add another constant pressure line for illustration. And that intermediate pressure, by the way, has a very specific value that we'll get to in a moment. But we're going to compress up to some intermediate point. We're then going to cool the compressed air down. In fact, we're going to cool it down to exactly the same temperature that we had at point 1. This is going to be point 3. And this cooling process, which occurs at constant pressure, is the process that we call intercooling. Okay? We're cooling in between compression stages. So in between, right? So between compression stages, we're providing the cooling. So this is the actual representation from 2 to 3 of the intercooling process. And then we're going to finish the compression up to the maximum pressure. And that's going to be point 4. Now, these state points do not correspond to the previous state points, obviously, when we're looking at the simple Brayton cycle. Ultimately, I'm going to add a regenerator into the cycle. I'm going to add reheat, which I briefly talked about. And then I'm going to have like 9 or 10 different thermodynamic state points. But for now, let's just look at 1 through 4 as being associated with intercooling and multiple stages of compression. Another thing I want to note as we first begin this is that in order to truly minimize the compressor work, we would have an infinite number of compression stages. But we can't do that. I mean, there's no way that it's going to be cost effective to have an infinite number of anything. And in fact, in this class, we're going to limit it to just one single intercooler with 2 stages of compression. Now, in reality, that's not going to be the most efficient. Certainly, if we continue to add compression stages with additional intercoolers, that's going to make it most efficient, but it's just not cost effective. In fact, what I found is that even if you try to add a second intercooler with another compressor, then already it's not going to be cost effective, because this all costs money, right? Yeah, we're going to improve the thermodynamic efficiency and therefore help maximize the power output or minimize the heat input. So that's certainly going to be our benefit. But if it's going to cost us hundreds of millions of dollars for all that extra equipment, we may never be able to recover that extra amount of money. So in this class, we'll just stick with a more realistic case. And that's the same thing the author does in the book anyway, a single intercooler with 2 stages of compressors. Now, why do we need it? Well, again, I'm just going to write down what I'd summarized before. This allows us to minimize, so this minimizes the compressor work. That's certainly one advantage to this particular process. Okay? I mean, even though we need 2 separate compressors, the total amount of work combined is going to be less than it would if we just had a single compressor. Another thing that this does is that it actually lowers the peak cycle temperature. And this is really more having to do with material problems. Okay. Keep in mind that the turbine is what's going to see the highest temperatures of all, right? Or let's say the discharge from our combustion chamber. Point 3 is going to be the maximum temperature. You get to a point where that is so high that we just don't have materials that can handle those high temperatures. So if we compress in stages, you might note, where's my diagram? Oh, here's my diagram. You might note that we're going to end up with a temperature here when we add heat, assuming that we add essentially the same amount of heat as we would have before. Adding heat from this point 4 instead of this point, which would be point 2 up here, we're going to end up with a lower peak temperature. Okay? And that's going to be good for materials reasons. Okay? It may not be absolutely best from a thermodynamic efficiency point of view. The higher the temperature, the higher the efficiency, but it's hardly worth it to build something with high efficiency if it's just going to break down because the materials can't handle those temperatures. So this is going to lower the peak cycle temperature, which is a good thing, at least from a materials point of view. And then another thing we might note is that as we're able to lower the temperatures in the cycle, doesn't that also increase the density? Right? Higher temperatures mean lower densities, lower temperatures mean higher densities. If we have higher density, then that means we can get more mass into an engine of a particular size, and therefore develop more power from that engine of a particular size. I mean, after all, the power is not just a function of the net work per unit mass, it's also a function of the mass, right? Lower densities mean less mass, higher densities mean more mass, and therefore more power. So the lower the temperature means we're actually increasing the density, and thus the mass flow rate, and therefore more power. So there's lots of reasons, really, why we might want to add intercooling to our system. Okay. So with all this in mind, what is intercooling exactly? So let me just see if I can spell this out. We compress in stages. And again, I'm going to refer you back to section 710. What we find is that to minimize the compressor's work requirement, we're going to compress in stages with equal pressure ratios. So we're going to compress in stages with equal pressure ratios per stage. In fact, we're going to use RP as pressure ratio, but we'll just put a further subscript stage to note that the pressure ratio in each stage is certainly different than the total pressure ratio, right? The total pressure ratio, RP, is the maximum over the minimum cycle pressure. The pressure ratio per stage is going to be the intermediate pressure over the minimum pressure, or the maximum over the intermediate pressure. But it's definitely going to be in equal stages, in equal ratios. Also, we would note that at the end of this process, we're going to cool. So intercooling from 2 to 3 results in the same temperature at 3 as we had at point 1. Okay? So T1 and T3 are going to be the same. Now, we might also note that I did indicate that here in the diagram. This is part of the compression process. If we have the same pressure ratio across each stage, and we have the same inlet temperature across each stage, then hopefully we'll see that we should also have the same temperature leaving each stage. I mean, whether we think about it in terms of variable or constant specific heats, it doesn't matter. I mean, just thinking in constant specific heat terms, we know that the temperature ratio for every compression process, at least the ideal compression, is equal to the pressure ratio raised to the k minus 1 over k. If we have the same pressure ratio across each compressor stage, it's still air, k is the same, so we have to have the same temperature ratio. If we have the same temperature going into each stage, well, we have to have the same temperature coming out of each stage. So not only will this intercooling lower the temperature at point 3 back down to the same as we had at point 1, we also note that T4 is going to equal T2. Okay? So again, T1 is going to equal T3, T2 is going to equal T4, and this is just the nature of, well, the intercooling process. Another thing that I should note, and this hopefully is clear by looking at that little diagram over there, that the intercooling process is done at constant pressure. So the pressure does not change from point 2 to point 3. That's just the intermediate pressure for the process. Okay, so intercooling is done at constant pressure. Okay. So hopefully this gives you a better feel for the nature of the intercooling process. Next, what I'd like to do is just try to find a relationship between the total pressure ratio and the pressure ratio across each individual stage. So what we can do is the following. So RP is just the total pressure ratio, right? It's just going to be the maximum over the minimum pressure in the cycle. Okay? Without the subscript stage, this would be the total. So we could just write this as P4 over P1 if we wanted to, right? P4 is representative of the maximum, and P1 represents the minimum. I can also multiply and divide by P3. This is just a very brief derivation. And then we would also note that intercooling takes place at constant pressure. So P3 and P2 are the same. So P4 over P3 times P2 over P1. Okay. Now, isn't P4 over P3 the pressure ratio across one stage? And isn't P2 over P1 also the pressure ratio across each stage? Remember, those are done at the same pressure ratios. So this is equal to the product of the pressure ratio across two different stages. In other words, pressure ratio across each stage squared. And therefore, we would note that the pressure ratio across each stage is just going to be the square root of the total pressure ratio. And again, I want to write the word total just to make sure that there's no confusion. So in a typical problem, you may not actually be given the pressure ratio across each stage. You may be, just read the problem carefully. But typically, you're given the total pressure ratio for that process, and you'll have to calculate the pressure ratio across each stage. And then once you have that pressure ratio, well, then you can just deal with the compressor like you would any other compressor. Okay, you'll find the work input to each compressor. Now, of course, the work input to each compressor is going to be the same. I mean, after all, if we have the same temperatures across each one, we have the same enthalpies across each compressor. And therefore, the work across each compressor is going to be the same as well. But nonetheless, I've just run out of time. So we're certainly not done talking about intercooling, but hopefully you at least have a better understanding for why we might use intercoolers for various reasons. And that's all then for today. Please don't forget, turn in the homework before you leave. So I'll just leave the big pile up here. I've got a couple of old homework sets. And I will see you all on Friday.